We're starting out strong. We will finish the same way. Is Jeff Lukas. Jeff is well known to this group, likely. For those of you who don't know him, he's a research integration specialist, impressive, with Western Water Assessment. The Western Water Assessment is a research program based at the University of Colorado, supported by NOAA, the National Oceanic and Atmospheric Administration. For the past 15 years, Jeff has worked closely with water managers and other decision makers to help them understand and prepare for climate-related vulnerabilities. He was the lead author in the 2014 Climate Change in Colorado report that was included in the Water Conservation Board's, for the Water Conservation Board and included in the Colorado Water Plan, summarizing the latest science on observed climate trends and future climate projections. Please join me in welcoming Jeff Lukas to the podium.
Thank you, Chris. Thank you to all the River District staff that made it possible for me to come out here again. Thanks to all of you for being here for the first talk of this seminar this year. So I was out here 2 years ago and gave, I'd say, a broad brush overview of our 2014 report on the impacts of climate change on water resources in the upper Colorado River Basin and across the state. So this will be a little deeper dive into, a very important aspect of that change and how it's ongoing now. And you could say both the motivation and really the outline for this talk came from who else? Eric, in his op-ed that was in the Sentinel in May. It covered a lot of ground. It's a very rich op-ed if you haven't seen it. But he said, it's looking more and more likely that warming regional temperatures have turned above average to abundant precipitation into just average runoff. Recently published science papers have zeroed in on this problem, and the consequences of warming on the Colorado River Basin are very serious. So how many people here have experienced or believe that in their basin watershed system that since 2000 they are seeing less bang for the buck, less runoff for the same amount of precipitation, annual or cold season precipitation or snowpack? So some of you feel like you're seeing that already. So we're going to, this kind of provides the motivation for what I'm going to discuss, and we'll try to dig in a little deeper into the details. So first, and this is a slide I showed 2 years ago, but to remind us that, we get a lot of rain and particularly snow here on the West Slope. Most of it, about 3/4, goes back up into the atmosphere before it reaches a stream or river. So we're dealing with the residual, and the atmosphere exacts a heavy tax. It pulls it back up before we can use it. And of course, we've got this wonderful snowpack-dominated hydrology. We accumulate the snowpack over the winter season, melt it off very quickly, and producing most of our runoff during a very short period of time. So that period of peak season, peak accumulation, and initiation of the snowmelt, as the snowmelt gets converted into runoff and the peak runoff, it's a very key time. It's only 3 or 4 months. And a lot is going on, a lot of different processes, and so that's where we're kind of focusing today, and we need to think about in terms of the future. So Colorado and the West and the country and the globe continuing to warm. You've probably heard that the last 2 years were progressively the warmest on record globally. 2016 looks like it's going to be on par with 2015, if not a little warmer. And we see this happening at the state level as well. So this is a graph that was in the 2014 report, and it was completed through 2012, which was the record warmest year in Colorado's history. And so I've tacked on the subsequent 3 full years and then 2016 through August. And we can see after 2 kind of closer to average years in 2013, 2014, 2015 was the 3rd warmest in the state's history, and 2016 looks like it's going to be right up there. And what's key is that in the past, the record warm years, you can see 1934, 1954, 1980, were also very dry years. And what we're seeing now since 2000 is that all years are much warmer than average, including in the last couple of years near average precipitation years. So that's a real signal of an overall warming of the climate. And it's not just the dry years, it's the average and wet years that are warm. And the summers in western Colorado are warming a little more than annual temperatures. And that's important because it speaks to the runoff season, it speaks to the irrigation season. And so I'd say, roughly in terms of annual temperatures, we've seen about 2 degrees Fahrenheit of warming in western Colorado over the last 30 years. So if we were used to kind of a late 20th century baseline, we've come up about 2 degrees from that since 2000. And summers, it's more like 3 degrees Fahrenheit warmer compared to 30 or 40 years ago. So, and this is, again, a slide I showed 2 years ago, and this is kind of my big arm-wavy kind of cartoon schematic where I say, hey, warming alone, regardless of what precipitation does, tends to dry out the landscape. A warmer atmosphere is kind of like a bigger sponge. It has the ability to extract more moisture from the land surface, whether it's soils, snowpack, open water, and vegetation. And so it's that evapotranspiration component going up. But in the talk I gave 2 years ago, I couldn't really delve into the details, and there's some new science that has come out about those details. So what is the impact of warming? And towards the bottom of that cartoon, you see runoff going down. What are the mechanisms by which warming tends to drive runoff downward? If we look at the observed record, and this is the reclamation's natural flow record for Lee's Ferry going back to 1906. I've got it through 2014 here. And it looks like both 2015 and 2016, when the official numbers come out, are going to be pretty close to 2014. So somewhere between, I think, 90 and 100% of the longer term average. But you look at all these wiggles, and it's really hard to pick out a warming signal by eye. We see a lot of drier decades and wetter decades in terms of runoff, really dry years, really wet years. It's hard to pick it out because precipitation, annual precipitation, is driving nearly all of the variability. And so in terms of looking for that warming signal, it's hard to pick that out from the noise of the background variability. So we use hydrology, or what are called land surface models, to understand all of the processes that relate the atmospheric warming to effects like decreased runoff, and to diagnose those effects that we can't easily observe. You have to go down and do field studies at very small scales to look at all of the different ways in which energy comes in and out of the land surface and the vegetation, the way that water comes in and out and actually gets down into the soil and the subsurface and makes it to the stream, and the way that snowpacks accumulate and then melt out. You can only do that at relatively small scales, and it's very hard to scale up to a basin-wide picture, which is what we need. And so we use these different models. If you have ever used a seasonal runoff forecast, how many of you have looked at a seasonal runoff forecast from NOAA, Colorado Basin River Forecast Center? You're using the output of one of these models, the SAC SMA model. So whether you know it or not, you've been using output from these models. It's the best tools we have to understand what's going on at a process level with the connection between the climate system and the hydrology. And so if we look at, there have been a number of studies using these hydrology models focused on the Colorado River Basin. We summarized several of them in the 2014 report. There's some others that did not make it in. I've extracted some nuggets from. The first is that the Colorado River Basin is more sensitive to warming impacts in general than other major river basins in the West, because that ET component, that tax, the 75% going back up in the atmosphere, is a higher fraction than most of these other basins. And that in general, when you have warming, you have this chain of less snow accumulation, earlier melt and runoff, and declines in runoff. That seems very clear in sort of the model world of the Colorado River Basin. And if you look very closely and ask what is that, quantify that sensitivity, you see that according to 3 of the most used models, the annual runoff declines by about 3 to 4% per degree Fahrenheit warming. If you include other models, they tend to lie a little further out in terms of the sensitivity, and that range expands to closer to 1.5% to 4.5% per degree Fahrenheit. So this implies that with our 2 degree Fahrenheit warming that we've had in western Colorado, that we've observed in the last 30 years, that we have already experienced and are experiencing a 5 to 10% overall flow reduction due to the warming effect alone, and up to a 20% reduction in the very warmest years, like 2012, relative to what we would have gotten in the past with the same amount of annual precipitation. And so what are the mechanisms that drive that? And here, some newer studies that I've listed, kind of help fill out the picture and add some more detail to my overall arm-wavy cartoon. First, we have in early fall and late spring, in a warmer climate, more precipitation falls as rain instead of snow. And maybe counterintuitively, rain tends to be a less efficient producer of runoff than snowpack. When it falls as rain and hits the land surface, it's more likely to be evaporated or transpired back up into the atmosphere compared to when it falls as snow. In a warmer climate, you get more sublimation loss directly from the snowpack to the atmosphere, though solar radiation, whether it's really sunny and windy, matters a lot too. And then when it's warmer, snowmelt initiates earlier in the season. And how many people have seen that in the last 20 years, earlier snowmelt and runoff? That's probably the most dramatic effect. And when you have earlier snowmelt initiation, the melt is slower. And again, maybe counterintuitively, the runoff is less efficient. You're not pushing out when the snow melts slower. It doesn't push out the water that's already in the soil, in the subsurface, to the stream as efficiently. A faster snow melt, so later in the season, when you get that nice flash melt in late May or early June, tends to provide a more efficient runoff than an earlier initiation of snowmelt. We have to throw dust in there too. I know you all have seen talks about the dust on snow impact in western Colorado, particularly in the southwestern part of the state, but it extends up to I-70 and northwards as well. And that we have a very good idea has been pushing snowpack earlier, particularly, or snowmelt earlier, particularly in the high dust years. So that's wrapped up in this as well. So both the dust and the warming are pushing the hydrograph in the same direction. And from what we see from these models, tending to lead to a less efficient runoff. And then once the snow is fully melted out, the soils that are exposed by that melt out can lose more moisture to evaporation over a longer snow-free season. And then similarly, the vegetation can start growing and greening up earlier, and you can get more transpiration loss. And then the same principle leads to higher crop water use when the temperatures are warmer throughout the growing season. So, okay, so these are the kind of mechanisms that the models tell us. What do we see in the real world? And there was a new study that came out earlier this year by Woodhouse and others, the title kind of says it all, increasing influence of air temperature on upper Colorado River stream flow. And what they did is a couple analyses of the observed stream flow record in the Colorado River Basin at Lee's Ferry. And the first was to look at the 2000 to 2012 period compared to other kind of decadal scale dry regimes of the last 100 years. And what they found was that while they all have similar stream flow deficits, they're all at about the 35th percentile relative to normal, or normal would be 50th percentile, so they're all about the same level below normal over that period. The 2000s had the highest precipitation of all of these dry periods and the highest temperatures. And so this was pretty good circumstantial evidence that the 2000s should have seen higher flow than these other periods, but the temperatures were knocking it down. So they went a little bit finer scale in time and looked at individual years and looked at those years with much different flows than expected given the October to April, the cool season precipitation. So I want to focus on just those kind of pink to red years. And you notice those are the ones where the flows, at least were below median, and they were much lower than expected given the precipitation that year. And you notice that there weren't many of them prior to 1980, and there have been a lot of them since then, particularly since 2000. So lower than expected flows given that October to April precipitation. And when you look at the climate, the weather of those years, and that's in that lower right-hand box, what stands out about them is they all had very high March to July temperatures. So during that 4-month box in which the snowpack is peaking, melting off, and you're trying to convert that to runoff as efficiently as possible. And so again, this is additionally, you could say, very good circumstantial evidence that we're seeing of this warming impact during the late spring, early summer, and that is causing us to have less runoff in the basin than we would expect given the precipitation. Similarly, this is a paper that's not yet out. It's in review by Brad Udall and Jonathan Overpeck. And similarly, they're looking at the Lee's Ferry natural flow record, and that's in the upper graph, and they've got a smooth on it in the blue that emphasizes about a 10 to 15 year time scale, both deviations above and below the mean. And in the brown, they've highlighted the low flow period that included some severe drought years in 1954 to 1966 versus the 2000 to 2014 period. And what they're seeing here is that while precipitation in the more recent period, since 2000, was higher on average than in 1954 to 66, and fairly close to normal at this point, if you can believe that, across that 15-year period. The flows in 1954 to 66 were about the same as they've been in the last 15 years. And in the lowest graph, you see that warming temperature trend across the whole upper Colorado River Basin. So again, good circumstantial evidence that we're pushing down flows relative to the amount of precipitation, especially when we're comparing to similar dry periods of the past century. So this is all, these studies are at a full basin scale, and we don't have as good measurements of the river, you could say. There's a lot more inputs, outputs, a lot more diversions and depletions and reservoir storage, when you're looking across the whole upper basin than at a smaller scale. So what I'd like to see, and hopefully I can actually participate in this myself, is some studies that look to see if we're seeing this impact at smaller basins that are more accurately gauged both in the precipitation gauge network and the stream gauge network. But the bigger picture is suggesting, yeah, we're seeing a pretty good impact right now, consistent with what the hydrology models tell us. And so then to the future, again, this is from the report, I showed this 2 years ago. All of the climate models and just basic physics tells us as emissions of greenhouse gases and other impacts of the atmosphere increase into the next several decades, that temperatures will keep going up, with the amount depending on the model you look at and the future emissions scenario. But another 2 to 6 degrees Fahrenheit of warming by roughly 2050. And so what that means, if we go back to the hydrology models and what they told us about the sensitivity of flow to the warming, is that implies a further Lee's Ferry streamflow reduction of 5 to 25% by 2050 from the warming alone. As you know, if you saw my presentation 2 years ago or read the report or read it elsewhere, we have a lot more uncertainty about future precipitation. Some models say it'll go up, some models say it'll go down. Kind of our understanding of the basic physics of the atmospheric circulation don't give us any more to go on. We kind of have to wave our hands and say, it could stay about the same, it could go up 5 or 10%, it could go down 5 or 10%. But really the key is that we're still going to get very dry periods, like a 2000 to 2004, or a 1950 to 1956. And when those low precipitation periods occur again in the future with an even greater warming tax on hydrology, and stream flow, the droughts will be even more severe. So even if our annual precipitation, we luck out, annual precipitation on average goes up a little bit over the next 50 years, it's not going to fully cancel out this warming effect because we're still going to really feel it during our droughts. And we would require, an annual precipitation increase of anywhere from 2 to 15%, depending on the warming in the future, to balance it out, again, on average. But we're still going to get hammered during the dry years and the dry periods with a warmer climate. And if you look at, again, a slide from 2 years ago, what I outlined is sort of the key climate change risks to the state and to the upper basin: a reduction in annual runoff, earlier runoff timing, greater ag and outdoor demand as the crop water use goes up, more frequent drought, that is, greater drought impacts with the same amount of precipitation, and then degraded water quality, because so many of those indicators and thresholds are driven by temperature change. Warming temperature makes them worse. All of these are driven in the wrong direction by warming alone. So we need to focus on the warming. It's unfortunate that the science can't give us much indication of which way precipitation will change, but we know it's going to continue to be very variable, both year to year and decade to decade. And so it's probably more important that we focus on what we have the most certainty about, which is the recent warming continuing on into the future. So in summary, precipitation drives that year to year and decade to decade variability we know and love and have to manage for, but temperatures matter. And the hydrologic models suggest we're already experiencing some reduction in upper Colorado flows, and new observational studies support this. I would like to see more evidence for it and hope to be part of studies to do that in the next few years. Future warming is expected to drive further and larger reductions in the flow relative to the precipitation. And the warming is also going to shift snowmelt and runoff earlier, increase crop water use, and exacerbate drought impacts. Kind of regardless of what precipitation does, we're going to experience that, at least in the drier years. So a final thought is that in a warming world, our snowmelt-driven system, think about that 4-month period I'm showing in pink in the lower graph, it's changing in ways that are difficult to predict from prior experience. Colorado has been this warm in the past, but it's been several hundred, if not a couple thousand years or longer. We haven't been around to manage our water resources through it. So we're in new territory with the temperature regime. And so things are going to change in ways that our models and our management approaches may not be calibrated for. And so they may be less accurate and useful in the future. And we have a new project where we're trying to dig into that in a couple different ways to talk to different West Slope water managers and providers about how they're currently managing for drought risk, using what indicators to make what decisions at what times, and looking with hydrology models to say, okay, how will these indicators, particularly things like April 1 SWE, how predictive will they be in 10, 20, 30 years in a warmer climate? And we'll be contacting, I believe some of you are already roped into this, and we'll be contacting some others of you to hopefully have you participate in this. I thank you very much for your attention. I hope we have some time for questions. And any questions?
How do you measure runoff efficiency?
Yeah, so how do you measure runoff efficiency? So it is calculated. It's just the fraction. So you need to have reasonably well gauged precipitation for a basin, and it's just the fraction of water year precipitation that runs off, that's in the gauge at the bottom of that catchment. And so that fraction can range in Colorado from, in the very highest subcatchments of like the Colorado River headwaters, it could be 50 or as much as 60%. For much of the state, it's 0 in nearly all years, no runoff. And for the upper basin, I believe it's in the order of, well, you saw western Colorado, it's 20 to 25%, depending on where you gauge it. Yeah, question in the back there, if you can yell it or get to a mic. Yeah, so that's a great point. Thanks. So are you from the Upper Yampa, district? And so in my previous research life, I did tree ring reconstructions of stream flow, looking back several hundred to as much as it. Yeah, sorry. So he is saying the Upper Yampa district has done risk analyses for drought using a 1,000-year tree ring record of past droughts in the Yampa Basin. And they've been criticized because those droughts are more severe if you look back before 1900 in the tree ring record than anything we've experienced in the last 100 years, even the 2000s drought. And what he's seeing looking at this is that maybe those paleo droughts are not as dire or extreme as those critics seem to think, that given what we're already experiencing from the warming and expect to see in the next several decades, that they're probably on target. And I think this is true, that you look at the worst paleo droughts of the last 1,000 years, and that's actually a pretty good proxy for what a 2000 to 2004 period will feel like with another 3 or 4 degrees of warming in 30 or 40 years. So I think using the paleo is not only expanding your perception of risk for today, but it's a pretty good preparation for what is coming in the future. Thanks.
One more question?
One more? Brett.
One of your first slides, I think it was showing the average annual temperature in Colorado, and you had the highest in 2012 and 2021.
Yep. We're getting there. Nope, overshot. Okay.
So the 4 highest years I noticed have very cool years immediately following. Is there any physical explanation for that? Can you repeat the question?
Yeah, so Brett is noticing that the 4 warmest years had, it kind of swung back to the normal, regressed to the mean in each of those years. Were not followed by really warm years. I don't know that there's a great physical explanation for that. And just thinking about kind of the mechanisms for climate variability, particularly ENSO, El Nino, La Nina, and thinking about those years, that's a neat observation. I don't really have a good explanation for it, worth looking into. Because that's one of the things, when you get into a 2012, you always worry, what if the next year is going to be as bad? And of course, 2013 felt as bad through the summer, and then it picked up. And so, in terms of temperature. And I think that's it. All right. Thank you very much.